Good afternoon, everyone. It is now my great pleasure to introduce Dr. Robert Key, our speaker for the joint seminar today. Dr. Key holds the John R. Brown Distinguished Professor of Engineering at Colorado School of Mines. His research efforts are primarily in the modeling and simulation of thermal and chemically reacting flow processes with application to combustion, chemical processing, electrochemistry, and material processing. So Dr. Key is the principal architect and developer of the ChemKey software, which is the leading software package used worldwide for simulating chemically reacting flow. So ChemKey has been the dominant modeling software in the field of combustion for more than 25 years. So the software's wide adoption stems from its strong code architecture that facilitates ease of use, as well as Dr. Key's extensive documentation that has been adopted and cited by thousands of researchers and developers worldwide as the seminal work in reactive flow modeling. Dr. Key continues to push the frontiers of reactive system modeling into new areas and is now acknowledged as an international leader in multi-physics modeling of electrochemical systems such as fuel cells and batteries and of multifunctional reactors for process intensification. Dr. Key has received many prestigious awards, including the Bernard Lewis Gold Medal of the Combustion Institute, the plenary lecturer of International Symposium on Combustion, the DOE Basic Energy Sciences Award for Sustained Outstanding Research in Material Chemistry, and the Bachelor's Award for Outstanding Contribution to Technology Transfer. So in addition to more than 200 archival papers, Dr. Key is also the principal author of the leading textbook, Chemically Reacting Flow. Now please join me in welcoming Dr. Key.
So thank you very much, Professor Lee, for a kind introduction. It's just wonderful to be here and sort of enjoy the beautiful fall weather with you in New Hampshire. What I'd like to do is share with you today some of the things that we're doing, mainly in lithium-ion batteries, both from the point of view of modeling the battery chemistry, electrochemistry, transport, and so on itself, and then incorporating that knowledge into process control. And I'll try to explain as we go how that's done. So Peter Weddle is a pretty senior PhD student now, doing a lot of the modeling. Huayang is a longtime colleague, is a research professor, and Tyrone Vincent is a faculty in electrical engineering expert in real-time control. So what are the objectives that I want to cover today? So first of all, I want to establish some fundamental understanding of how a battery works, how it's put together, and so on. Again, there's lots of kind of batteries. I'll focus on lithium-ion. We're going to be able to predict performance, assist the interpretation of experimental data, such as with electrochemical impedance spectra. Important aspects of what we're doing now and looking forward are the real-time state of health monitoring, sort of predicting in advance where a battery may fail, how to take corrective actions, and so on, and to do optimal control to meet demand load, but optimize other things like battery safety, battery lifetime, and so on. So what I'll talk about today first is showing a little bit about how we look at the electrode microstructure for the purposes of deriving properties that then go into full battery models. We'll then upscale the microstructural understanding to the cell scale. We'll then take large models, million-state models of batteries, and reduce them using so-called Statespace models, which can then allow us to use those state-space models to recover measurable impedance spectra and to incorporate physical knowledge into model predictive control. And again, I'll focus on lithium-ion batteries. Let me first just introduce you, if you're not already familiar with, say, an 1860 format lithium-ion battery. This is the positive terminal, and in some limited time here, I won't explain all the safety features, but if you take apart a lithium-ion battery and look at the cathode, you'll see a lot of interesting features that are in there specifically to facilitate safety. We can come back to some of these things if there's time at the end. Almost all, not all, but the dominant literature looks at the electrodes as agglomerations of spherical particles which can intercalate and deintercalate lithium as the lithium-ion shuttles across the separator. Here are some SEM images of an NMC cathode taken by my colleague at Stanford, Will Chu. What I want to show in the next slide is a realistic picture of what these electrodes look like, and as recovered by FIBSIM, focused ion beam scanning electron microscopy. So we can take these batteries apart and then reconstruct the actual electrodes. And so if you look at this actual electrode on the tens of micron scale, I would say nobody would look at that and say, gosh, that just looks like a whole lot of spheres put together, right? I mean, it just doesn't look like that. So one of the things we want to know is about the transport, especially, and the electrochemistry on this microscale in a way that we can use that knowledge when we build models of the full battery, which quite obviously cannot be resolved at this scale if you're modeling a whole battery or a whole pack of batteries. So let me just take a minute, if you're not already familiar with FIBSIM, and I think there are people here who are. So we'll take commercial batteries, unpack them in a glove box, unroll the jelly roll, which have the membrane electrode assembly in them, and then ion mill several hundred times to get these two-dimensional images, which then with software can be reconstructed. Actually, we just talked with one of you at lunch, one of the students at lunch, about that reconstruction. This is so mature now in medical imaging that it's almost a laugh. We light up the software to do this reconstruction, and the user interface wants to know who's the attending physician, what's the hospital, and so on, because that's just where the software comes from. Anyway, let me just, before I forget it, so this person, Graham Golden, is your neighbor. He's sitting here in the middle of the, works at CD Adapco and does a lot of work on battery modeling. Okay, here's just a quick image on how the FIBSIM works. This is a focused ion beam SEM. You use a gallium beam to mill a face, take an SEM picture, mill it back another 100 nanometers or so, take another picture, do it a few hundred times, then just deliver these hundreds of images that I showed on the last slide to software, which reconstructs the three-dimensional microstructure. We then mesh. I mean, these are very large simulations on a very small piece of real estate from the battery. But we can mesh this and look at the electrochemistry, look at the transport, and so on at that micro scale. So I'm not going to say much more about that. I mean, that's a talk in its own right that I want to move past here. But once we've meshed it, then we actually go to commercial software. In this case, go to ANSYS, which again is your neighbor in Lebanon, as I'm sure everybody knows, and solve this electrochemistry problem on this microcube. I say almost a little bit tongue-in-cheek, if you look at these equations and you go, yep, that's right, okay, we're done. If you look at it and say, where in the world did that come from? you're not going to learn it in this lecture. It takes too long. So we're going to solve an electrochemistry problem on these microcubes. This is one such result where we're looking at local temperatures as we discharge a battery. And you'll see high temperatures relatively just around the peripherals. We've put a little bit of a short in here, so as the ion current is necked down toward that short, you see some local hot spots and so on. One of the important things that we derive from these models is things like the effective conductivity, right? So we've got a very complex microstructure here, but if we're asking the relatively simple question of what is the average or the effective conductivity through that composite structure, it turns out even though the geometry is very complex, the computation is actually quite simple. And you can solve that, okay, on a big computer, but in a few minutes. I mean, that's a fairly rapid calculation. And from looking at the actual fluxes through this microstructure, we can derive what the effective conductivities are. And that's actually quite useful to map that actual microstructural architecture back into the into models of the whole battery. What's difficult to do, and frankly we haven't really figured it out, is how to map the internal heat generation back to the big model. Okay, so with that kind of background at the microstructure, let me take a huge step in length scale and talk about modeling whole cells. These are prismatic cells where we're showing temperature distribution under some discharge conditions. I'll point out that this simulation was done using ANSYS software, again, your neighbors here. This simulation, where we're looking here at hot spots around the tab, was done with CD Adapco, also your neighbors here. So you guys are really well positioned in this space to have very knowledgeable neighbors in the battery space. Here's one simple example. We worry a lot about overheating then leading to accidents. I mean, I haven't seen one in the news recently, but Boeing Dreamliners had accidents that sidelined those airplanes for many, many months. Galaxy something or other telephones were catching on fire. I mean, these are real issues. It's not like your laptop catches on fire regularly. In fact, probably nobody in this room has ever had a laptop catch on fire or a telephone. But it is a real issue to make sure that these things are safe. So we're quite keen to know what happens if, for example, we have a dendritic short someplace in this battery, how that thermal response propagates and leads to accidents. What I'm showing here again at the macro scale or micro-macro scale in a jelly-rolled structure is if I look at the effective conductivity radially, then these foils have almost no effect because the resistance, the thermal resistance of those metals is very low. There's basically no resistance. So the radial heat conduction is driven essentially entirely by the conduction of the electrodes. But in the axial direction, it's quite different because now these metal foils, the current collectors, can channel heat axially much, much more efficiently than radial. So when we look, here again, I've taken a battery and just arbitrarily produced a short. In other words, a local hotspot in that battery. And so what you see here is that compared to assuming isotropic properties, in fact, they're anisotropic properties, and because of the role of the foils, of the current collector foils, you preferentially transport the heat axially and less so radially. And that has a big effect on the time at which it takes to come to a thermal runaway or some other accident event upon an internal short. I take two slides here as a little bit of a detour, but actually at least an interesting detour. So this is in the chemical-mechanical coupling. So here is a lithium cobalt oxide particle that we've extracted from this three-dimensional structure I showed. We just extract an individual particle and intercalate it. And what I'm showing here, actually rather old data from Reimers and Don, that shows, yeah, let me come to here. As you intercalate lithium into this cobalt oxide, at first there's a monoclinic phase, then there are actually two hexagonal phases as you intercalate or as you reverse back toward in the case of charging. What's interesting about this is if you look at the lattice spacing, there's actually a considerable change in the lattice spacing as you intercalate, and it goes in a direction opposite from what you might think. You would intuitively think as you push lithium into this matrix, it would blow up like a balloon. In fact, that's not what happens. The lithium, since it's positively charged ion, it tends to attract the cations, the oxygen, the anions, and so it actually shrinks a little bit, and a fairly substantial difference between the lattice volume between these two hexagonal phases here. So what happens, in fact, then, is that in crack-like features on this cobalt oxide, you have stress risers near that crack, and they tend to be tensile. And so as you intercalate, that tends to work cracks and open them, which is not what you want to happen. So I'm showing here an image that we did together with Scott Barnett at Northwestern, where in this case is not a FIBSIM, but it's an X-ray tomography, where we put a cathode and did X-ray tomography and looked at places that were initially quite well connected. Then cycle the battery, like not many times, like 10 times, and what you can see is places that were intact are now floating free. That's one of the reasons you have capacity fade in your battery. If this particle splits off and it loses electrical contact, then there's no way to make the charge transfer chemistry run, and that little bit of cathode is basically useless. And if that happens enough, your battery doesn't have the same capacity as when you originally purchased it, and everybody's familiar with that paradigm. You buy a new battery at some point. There are other reasons for capacity fade. That's one. Okay. With that kind of background on modeling the batteries alone, let me shift now to how we take some of that knowledge from modeling the batteries in sort of large-scale modeling. How do we incorporate that knowledge into things like control? So much of our work is supported by the Office of Naval Research for the purposes of battery packs within these UUVs, unmanned undersea vehicles, which almost invariably are just full of batteries. I mean, 1,000 batteries in there. They're often assembled onto blades that look like this, where you have diagnostics, electrical diagnostics and thermal diagnostics on the blades. And one of the things we want to do is to be able to incorporate some knowledge of how these batteries work into the power electronics and into the control scenarios. And I'll talk about that in the next few slides. Okay, so a central connecting block between, let me just call it large-scale physical models. I mean, these can easily be million-state models, finite volume representations of thermal, electrochemistry, and so on. And we want to do a number of things like interpret the complex impedance, implement model predictive control, look at state of health monitoring, and so on. And this sort of, in some sense, rather innocuous looking mathematical statement of a state space model is the bridge. And I'll say a lot more about that in the next few slides. But this is a locally linear model. And so you should rightly ask, come on, how can a linear model possibly represent a battery which is quite obviously nonlinear? And I'll try to explain that as I go on, but it can, but with some twists. So assuming that I need this state space model as the bridge between the physical models and things I want to do, I want to now talk about how do I get this state space model. So, okay, that's not what I want to say next. I'm simply representing here what the battery management system looks like, which in our case will be a state space model and some power electronics, which facilitates perturbing the loads and so on in a way to derive, to understand the physics. And with actual sensors, actuation back to the system. Okay, that's just kind of a cartoon picture. Okay, let me come to the state space model. By the way, I'm just curious, how many people know what state space modeling is? Is that something we talk about here very much? Maybe a few do. Anyway, so if you already know, this next segment is sort of sophomoric, I suppose. If you don't know, hopefully you'll mostly get it. Okay, so here's a state space model. X is called the state vector. It's an abstraction. You cannot associate an element in that state vector with something physical, like temperature, voltage, or something like that. It's an abstraction. In some sense, you could argue that's a downside of such models, but it is what it is. U is the actuation vector. So if I'm controlling the current in charging or discharging a battery, then U is that current that's actuating the device. Y is the observable. So for example, I actuate current, but I observe voltage, temperature, maybe other things. But that's the Y vector, the observable. And D is basically disturbances and various things which sometimes come in. So what I need to do is identify these matrices. And once I have those matrices, I then have a state space model, and it's a locally linear model. As an aside, much control or much interpretation of batteries is done with equivalent circuits. And that's a fine thing to do, but it also suffers the idea that it's hard in many cases to unambiguously assign the value of a resistor to a particular chemical phenomena. Say it's electrochemical charge transfer rate or something like that. There's an indirect association there, although equivalent circuit models are very, very widely used. We think that representing it with state space models has some very significant advantages compared to equivalent circuit models. So even though the state vector is an abstraction, the observable is not. And so these models predict observables, and we'll use that to interpret sensors in the control. Here again, if you're familiar with impedance spectroscopy, which is just practiced everywhere in electrochemical devices, whether it's fuel cells or corrosion or batteries or what have you. What we're showing is the impedance in the complex space. These are frequently used, in fact, almost invariably used in every electrochemistry lab to represent electrochemical behavior as the complex impedance associated with the device. What I'm just showing here are particular impedances that are for a particular battery at different states of charge, and I guess just specifically that, different states of charge, whether it's charging or discharging. In other words, the impedance tells you a lot about the state of charge of the battery. So again, at the risk of saying things that are obvious, if they're already obvious to you, what is the impedance? Well, as you say, harmonically perturbs, say, the current onto an electrochemical device, the response, say the voltage, is shifted both in amplitude and in phase. And if you look at this picture, the complex impedance, this angle theta is the phase shift, and this Z here is the amplitude change. And you can plot that as a Nyquist plot in the complex space, and that's what an impedance spectra is. But it carries a whole lot of information that we'd want to interpret in the operation of the actual device. Okay, now, in some ways this almost seems like cheating, but because that's so important, I mean, basically every electrochemistry lab in the world has an impedance spectra. I mean, that's just everywhere. And so it's so important, and it's basically linear algebra manipulation. So someplace, yeah, so all this stuff is automated in MATLAB, meaning if I've identified the state space model, which I haven't yet said how I'm going to do, that's coming in just a minute. But once I have the state space model, meaning I have these A, B, C, and D matrices, then literally you go to MATLAB and say, give me the Nyquist plot. Now, of course, there's mathematics underneath that, which I've represented here, but it's simply a bunch of matrix manipulations, and it's automated. So the state space model, once I've identified it, gets me instantly to the impedance spectra, which can then be used to assist interpreting experimental measurements in the laboratory and so on. Okay, so now I come to, fine, I need a state space model. How did I get it? Well, there's two ways, there's probably more than two ways, but there's at least two ways that we use. So let me come here first for a method that we mostly do not use. But if I have a physical model, I mean, if I really have the physical model, and I can differentiate it, and I'll show what I mean by that in the next slide, then I can derive from the numerical differentiation of this big model the state space. That's easier said than done, partly because if we're using large-scale models, such as I mentioned from CD Adapco or from ANSYS or something like that, we don't really have access inside the software to extract the matrices we want. I mean, the user hooks just aren't there to do it. In our own models, we can differentiate them because they're our own models and we can do anything we want with them. And I think I'll say in the next slide a bit about this. But what we really do is look at the physical model as a black box. And we do what's called pseudorandom binary sequence perturbation, which I'll explain in more detail in a few minutes. Okay, this is what I said in words just a minute ago, again, in a pretty abstract way. If you assume this is a big model of a battery that may be 1 million states that I can differentiate, I can extract these matrices. Let me just leave it at that because it's not really what we do. unless we're just working on our own models. Okay, so let me come back now to a full battery model. And let me say there are many, many parameters in a battery model. I mean, what are the thicknesses of these electrodes? How thick are the collection foils? Where are the tabs done? What are the material properties? What's the microstructure of the electrodes? There's what are the diffusion coefficients of lithium ions in, say, ethylene carbonate electrolyte solvent? I mean, there's literally hundreds of parameters to define a particular cell. And so one of the tools that we use is coming from CD Adapco, or actually more directly from a company called Battery, I can't remember what's Battery Design Studio is the software. Is that also the company? And anyway, it doesn't matter. So part of CD Adapco is they've got a couple of batteries that are very, very well defined in terms of the space. And this is just showing a user interface where it gives you the opportunity to literally put in hundreds of variables to define a battery. And in a few batteries, we use a Sanyo 1500 milliamp hour battery that's been very well characterized for a lot of what we do. Okay, so interior to the software like Battery Design Studio are a number like 20 so-called Newman models. So John Newman, professor at Berkeley, published this general approach to modeling batteries, one-dimensional models, in I think the first paper was 1993 or so. Okay, so a long time. But those are the dominant models in the lithium-ion battery space. And what this Battery Design Studio does is lay out the full architecture of the battery and then implement roughly 20 of these models interior to that battery, which then gives the overall performance. This is our own representation. I mean, many people have built essentially replicas of the Newman type models. And as I said earlier, I'm not going to dig into the mathematics of that. Okay. Now, how do the PRBSs work? Well, we take, again, call it, roughly speaking, a million state model, and we perturb it with small current steps in the milliamp range. Okay, so small current steps that are of different duration, but usually the same magnitude. So then we drive the physical model with these perturbations and observe the response. In this case, I'm simply showing the observed response in the voltage, but we also look at temperature and other things. And because this is so widely practiced in the control literature, again, MATLAB has automated those tools. Again, I can go into the mathematics of that, but as a practical matter, I take this input stream, drive a physical process with this input stream, observe the response. I now have two long vectors, input, output. And there may be multiple outputs, there may be multiple inputs. And again, at this minute, I'll just make it almost like magic. You present those two wave trains to MATLAB, and it delivers you these matrices. I mean, again, it's so widely practiced that it's been automated. And so you don't really, any individual doesn't really have to go write that software. It's just already been written. It's probably worthwhile to understand it, but you don't have to write it. It's done. Okay, now, as a practical matter, it's better to identify the models under different frequency ranges, right? So batteries have some very low frequency behavior, mostly diffusion of ions within the electrolytes, and they've got some high frequency behavior like the charge transfer chemistry and so on. So it's usually better to identify the models in different frequency ranges. Then we use what are called stitching algorithms. I put some of the mathematics up here, but you use so-called stitching algorithms to take the PRBS identification at different frequencies. We typically run 3 or 4 different frequency ranges and then so-called stitch the state space model back together. Now, if you were taking the physical model and numerically or even analytically differentiating it, you wouldn't have to do this. You would just get the matrices straight out. But as a practical matter, it's more accurate to identify in frequency ranges and then stitch the state space model back together. Whoops, that's interesting. I don't know why, but so there's nothing on my screen and there's nothing there. Okay, try. Okay, I don't know why. Oh, it's there. Okay. Okay. All right, I think I might have skipped a slide there, but it's probably fine. Oh, okay. So I just talked about stitching, which takes identified models under different frequency ranges and puts them back together as a single state space model, but at some operating condition. What I'm talking about now is so-called gain scheduling. So remember, we've got a nonlinear system, the battery, and I've got a linear model. Well, on the face of it, that doesn't make any sense, right? I mean, the battery is plainly nonlinear. How can I possibly have a linear model that represents it? And the answer is you can't. So what you do is you make multiple linear models. And for like these kind of batteries, typically 10 or so linear models can be used in combination to represent the nonlinear behavior. And I'll show that works here in a minute. But that's called gain scheduling. So for example, we'll identify models, just shown here, one at 25C at different states of charge. Here's at 45C, different states of charge, and so on. And so we'll do many of these under different operating points. Then, again, without getting into the mathematics, you use what's called gain scheduling to intelligently interpolate between these multiple locally linear models. This is all very well understood and widely practiced in the control literature. So I'm actually going over that fairly quickly, but this is what we do. So you first of all stitch and then you gain schedule. So take a look at this. Okay, so here is some current demand over an hour of time. Okay, so what we're doing here is charging, discharging, and so on. So this is a demand curve that we're asking the battery to deliver. So if this is a motor, I may be accelerating or decelerating, I'm charging, I'm discharging, I mean, it's in some sort of a hybridized system perhaps. But this visits a lot of space. So the dots here are the gain scheduled linear model. The lines are the are what this big million state model is doing. So it's model against model, but one is like a 20 or 30 state gain scheduled linear model, and the other is a million state model of the full battery. And is it perfect? No. I mean, there are some places here where there's some departures, but actually that's very, very good. So we've got linear models that can be solved very, very quickly in their own right. It enables optimization and so on. So, and we've done many of these. I mean, these gain schedule models are just very good representation of the actual physics. Now, what's one of the advantages of having locally linear models? Well, it turns out that you can solve this exactly. I mean, you just solve this exactly. Now, you need to deal with some convolution integrals and things like that, but you can solve it exactly. And in a sampling space, in other words, you're in a controller where you're sampling the sensors every second or every 10 seconds or something like that, you can solve this problem in a discrete sense just by doing some matrix algebra. I mean, it's actually very straightforward and very fast, and we're going to take advantage of that. So let's look at a couple of examples of things that we want to do. So here's a physical plant, a bunch of batteries, for example. We've got actuation, meaning we tell it we want a certain amount of current draw. And we've got sensors. We're measuring temperature, we're measuring voltage, but we've got actual sensors. Then we need a model predictive controller that decides based upon these sensors and based upon what the model, what the Statespace model says the sensors should read, we're going to make decisions about the next step for the control. And I'll show other examples of this, but we're also it's very important to obey constraints. So for example, I want to stay out of this region where we would have lithium plating. So as the temperature goes down, it limits the voltage I can charge at, and things like that. So the model predictive control enables the respect of constraints. So things like PID control, for example, cannot. Right? There's just no way to impose constraints with, say, a PID controller. But a model predictive controller, you can. Okay, so I'm going to spend a couple of slides trying to explain that in a little bit more detail. So here's a physical plant. We read the sensors. So here I'm just assuming, let's say, measure temperature and voltage. And those are real sensors that I'm going to call Y observed. So Y is the observable, and I'm actually reading some real sensors. Then I'm going to do a so-called moving horizon estimation where we first bring in the actual readings, voltage, for example. Then I need to determine the operating point. In other words, what is the state of this battery? What's its state of charge? What's its temperature? And so on. I need that information in order to go back to the gain scheduled model to know how to blend between these various linear models. I'm then going to solve the state space model to predict states and observables. I'm then going to change the state. This is sort of like revisionist history, but this is how this works. I'm going to change the states in an orderly way so as to minimize the difference between what the model said the sensors should read and what the sensors actually read. And so that, I think, is sort of intuitively understandable. We're also going to adjust the states to minimize the modeling error, which is less intuitively understandable. Then that information gets passed over to the controller, which ultimately decides what the actuation should be for the next step of the controller clock. Okay? So that's said kind of in words. I won't spend much time on this, but the words I just said can be manifested mathematically. I mean, these are operations that we can do, and despite the fact that the mathematics may or may not look complicated, it's actually fast, and easily programmed. So this is a representation of the last slide I just showed, but now in graphical terms. So the estimator, Kalman filter if you like, moving horizon estimator, is an iterative loop. And so what happens is we look at the error between the actual sensors and what the model says the sensors should read. And they're not naturally never the same. This is a relatively simple model, and we're not controlling on the model. We're controlling on the sensors, but we're using the model to interpret the sensors in an intelligent way. In addition, which is, it takes a while to get your arms around this one, but here's some estimate of the current states. We can then solve, even retroactively, if I have this state and I've got the model, I can predict what the steady state solution, the Statespace solution is for each of these prior states. And the estimator minimizes the sensor error and this model prediction error by changing the historical states. That probably seems odd to you because the historical states are whatever they are. But in order to look forward, it turns out that these moving horizon estimators actually go back and revise the earlier states in a way to make a better prediction of the future. So that iterates until it satisfies some convergence criteria. Then there's an within the control that minimizes the difference between what the model says the observable will be into the future compared to the objective of what you want the result to be. So in other words, you want to look ahead and have the controller change the actuation, change the actuation to some objective function, battery life example, or any number of things. Okay, so let's look at a couple of quick examples. We're going to look at two charging scenarios. One I'm going to try and completely charge in 800 seconds, another one in 1500 seconds. And the objective is to maximize the end state of charge. In other words, I want to fully charge the battery in some amount of time, but I want to respect some constraints. In other words, I don't want to charge so fast that I overcharge and cause a dendrite growth or some other damage to the battery. I mean, that's one of the failure modes of battery, is overcharging. So I'm going to impose two constraints. One is a temperature voltage constraint, one is a voltage constraint. We're going to actuate the current, and we're going to assume that we've got sensors that measure bulk temperature of the battery and the terminal voltage. So here's a discharged battery that's sitting here at 3.6 volts and 25 degrees. The controller is, so this is now running a controller. It's not explicitly controlled by me. This is under now control of this model predictive control. And what we see is charging. As the battery charges, of course, the voltage goes up and the temperature goes up. But at this point, we run into a constraint that says if the temperature is what, the voltage, you can't exceed a certain voltage. Right, so smart chargers need to respect these constraints because you can overcharge, you can make dendrites, you can have all kinds of problems. So then what happens is to stay on this constraint, but we still want to keep charging, then the controller rides down this constraint until it hits another constraint that says, I don't want to charge above 4.15 volts, because that would also be a damage mechanism. So what happens in these two scenarios is that so the controller up to this point basically follows the same trajectory. Then what happens here is that the voltage is measured based upon the lithium at the peripheries of the electrodes. In other words, the charge transfer chemistry doesn't know about where the lithium is within particles. It only knows what the surface is because that's what drives the charge transfer chemistry. So what happens here, if I stop charging at this point, then the lithium continues to diffuse into the interior of the particles. So you think you're fully charged here in this fast charging. You think you're fully charged here, but you're not. The peripheries of the electrodes are fully charged, but the battery itself is not fully charged. So then you stop charging, but as the lithium then diffuses into the interior of the electrodes, the voltage now relaxes. So you weren't really fully charged. In the second charging strategy, we come to this constraint, but we continue charging at constant voltage, and then that fully charges the battery, brings it to 100% state of charge. Anyway, that's just one example. I'm going to jump quickly here to another example that now we're charging a bank of batteries that start with each of the batteries at a different state of charge. So you may or may not want to do that. I mean, there are reasons why you want to charge and discharge batteries in a bank differently. The important part I want to make here is that the constraints now are on overpotential and intercalation fraction. But there are no sensors to measure either. You have no way to measure overpotential. You can measure electric potential or electrostatic potential, but you can't measure overpotential, and you have no direct measure of what the fraction of lithium in say, a cobalt oxide is. So what we're doing here is controlling multiple batteries, but also controlling to sensor inferences, not sensors directly. Okay, let me just say very, very briefly, one of the things we're keen to do, and this is work with Corey Love at the Naval Research Lab, is to look at single frequency impedance. So rather than do an impedance sweep over all frequencies, we'll look at, say, 300 hertz or something like that. And what Corey has observed experimentally is that as a battery is damaged or otherwise aged, then you get impedance shifts. And what we're trying to do is to build that knowledge into the controller. So we see a shift in frequency to try and assign that to some physical behavior, such as an overcharge event, and then control to that. So in this case, what we want to do is take, say, a power demand curve, but instead of simply delivering that power to the motor or whatever the end use is, we'll put essentially a carrier frequency at some frequency, and then interpret impedance shifts in terms of battery damage or something like that, and then take corrective action before there's actually a problem. I'm going to jump over all this and I'm just with one eye on the clock. I think it's time to close. So let me just summarize by saying that to really understand battery technology, we really need to understand physical processes over actually very wide ranges of time and length scales. Okay, that's almost a hackneyed comment anymore, right? I mean, everybody's talking about disparate time scales and so on, but it's certainly the case in batteries. So we do, I showed some images of actual reconstructed electrodes. I talked a little bit about these so-called quasi-one-dimensional membrane electrode models, the so-called Newman models, how that gets then embedded through, say, Battery Design Studio into full cell scale models, which are fine in their own right in the sense of design. But in terms of control or sort of more real-time things, we need to reduce those models, and we reduce them through state-space modeling, which is, again, the bridge, if you like, between large physical models and small real-time models. We then use those state-space models to enable the interpretation of measurable electrochemical impedance, to implement model predictive control, optimal mission accomplishment, for example, state of health monitoring that I just talked about very, very briefly. And the model predictive control allows us to evaluate alternative strategies in terms of charging, discharging the batteries, respect constraints such as dendrite growth or overcharging scenarios. And so this brings us to what we're really very actively doing now, is integrating with the battery management system so that the power electronics can implement some of those features here. So let me close with saying that most of our bills get paid in this space by Michelle Anderson at the Office of Naval Research, CD Adapco, which is again your neighbor. Graham is sitting here. Northwestern, I showed some of the FIBSIM work in terms of electrode reconstruction. ANSYS, also your neighbor. Eric is here. I don't know if Ganong's here as well. So again, everything I talked about, all you have to do is walk down the street and you can find some other real experts on this modeling business if you want to be in this space. And then I mentioned some of the work at Corey Love in terms of the real-time state of health monitoring. And with that, I'm happy to welcome questions if there are some.